Welcome back. We're going to continue in Chapter 10, our 6th unit of the year. Today's learning targets are: I can find the probability of independent events with replacement. I can find the probability of dependent events, that means without replacement. Have these in your notes for tomorrow. Probability of independent and dependent events, Section 10.5. Here we go. Probability of independent events. Probability of A and B equals P of A times P of B, or probability of A times the probability of B, or you multiply the probabilities. Two events are independent if the occurrence of one has no effect on the occurrence of the other. Notice, this is different than the union probabilities. A or B, we added them, right? And as intersection, we multiply. So here is a example. P and A, or excuse me, two events, A and B, are independent. If the probability of A is 0.25, and the probability of B is 0.3, find the probability of A and B. Well, if they're independent, then we take the probability of A times the probability of B, 0.25 times 0.3, which is 0.075. Okay, here's an example of one that maybe has a little more real-world meaning or applications that just raw numbers. You have a color wheel with different colored wedges. There are 8 blue, 3 yellow, 7 green, and 12 red wedges. What is the probability of spinning a green, then a yellow? So as we get going and we discover dependent probabilities, we're going to have to ask ourselves this question, so let's practice now. Does spinning the first spin influence the second spin? And the answer is no. Whatever you spin the first one does not influence the second time you spin. So 3 yellow, 7 green, and 12 red, and 8 blue. So we want to spin a green. There are 7 greens, and there are how many total? Well, we have to add them all up. 7 plus 3 is 10. 8 plus 12 is 20. 20 plus 10 is 30. So 7 out of 30 times yellow. 3 out of 30. So we multiply that out, we get 21 out of 900. So we just multiply numerators times numerators, denominators times denominators, which reduces to 7 out of 300. You can also approximate that as a decimal. Okay, 2 cards are drawn from a deck with replacement. When you see the word with replacement, that means you put it back. Okay, what is the probability of drawing a spade and drawing a 5? These are independent events as well, because if you look at the card and then put it back, you still have the same amount of cards you started with. So what is the probability of drawing a spade, then drawing a 5? Well, there's 13 spades out of 52 cards. And there are 4 5s in the deck, so 4 out of 52. Reducing these before we multiply, spades are 1 out of 4 suits. 5s are 1 out of 13 types of different cards. We multiply together, we have a 1 out of 52 chance of picking a spade than a 5. Okay, every morning one student in a class of 24 students is randomly chosen to take attendance. What is the probability the same student will be chosen 3 days in a row? This is independent as well because it doesn't say that they can only do it one time. So they just randomly pick 1 out of 24 students every day. So 1 out of 24 times 1 out of 24 times 1 out of 24. So we can apply this independent formula to more than 2 events. So you get 3, 4, 5 events. If they're all independent, we just multiply the probabilities together. So that's 1 out of 24 to the 3rd power, or just 1 out of 13,824. If you get a decimal for that, the likelihood of being picked 3 straight days, well, it's about like playing the lottery. Not very good, as you can see. Way less than 1%. Okay, during a high school track meet, each race consists of 9 competitors who are randomly assigned lanes from 1 to 9. What's the probability the runner will draw 1, 2, or 3 in the 3 races in which he competes? So, probability of 1, 2, 3, and 1, 2, 3, and 1, 2, 3. So this apparently is a runner who he or she really likes to be in the first 3 lanes. Okay, so, well, the probability of being 1, 2, or 3, well, they're all independent if it's randomly drawn. So 1, 2, 3, that's 3 lanes out of 9. So 3 out of 9 times 3 out of 9 times 3 out of 9. We can multiply that in our calculator and then reduce it. If you reduce them each before you multiply, then you don't have to worry about it when you're done. That's 1 out of 27. Okay, so we did a bunch of examples of independent events. Now let's look at some dependent events. Two events are dependent, there we go, if the occurrence of one affects the occurrence of the other. Okay, so this is a with replacement situation. Okay, and the formula P, probability of A and B, is the probability of A times the probability of B given A. This is the probability of B given A. That's how you say that. So it's really the same formula, it's just we have to take into account that A happened and it's going to influence the second event B. Okay? So down here, another way to look at it, probability of B slash A is the conditional probability of B given A. So you can see it written out a little more neatly than I did in blue there. Examples. Example A and events A and B are dependent. The probability of A is 0.15 and the probability of B given A is 0.75. Find the probability of A and B. So it's not like the last situation. We multiply the two together. It's just sometimes when we get to a real world type problem, it's a little trickier sometimes to find that probability of B given A. But we multiply them together. There's the basic one. If they just give you the numbers, 0.1125, you can approximate that as a fraction as well. Okay, so here's another situation. Maybe you're given a table of data, and you're gonna be asked to find probability given some situations here. A listed person has blue eyes. Well, there are 35 males with blue eyes and 9 females with blue eyes. So 35 plus 9 out of, well, how many total people are in this list? If you add it up, there are 100 males and 100 females, so that's 100 plus 100 or 200. So 44 out of 200, which would be 11 out of 50, or 20.22. What about a male that has blue eyes? A male has blue eyes, well, that's 35 males. Okay. So you have to be a male and have blue eyes. Well, there's only 100 males. 35 out of 100, or 7 out of 20. We didn't do it out of the total because we were given that it's a male and they have blue eyes. Okay. How about given a female and she has hazel eyes? Well, females, there are 41 females with hazel eyes out of 100 that can't reduce. Okay. So there is using a chart that may happen as well, especially with real world data. You'll be given a chart and find probabilities that way. So let's find the probability that an integer randomly chosen from the integers 1 through 50 under 10 is a given event. I'm going to leave that one for you guys. We're going to go to the next example, okay? But that's one for you to practice, okay? We're going to compare independent and dependent events. So now we have to look at it and see how it differs. Sometimes they're very close, but there is going to be a difference if events are dependent or independent. So let's look. Randomly select 2 marbles from a bag containing 15 yellow, 10 red, and 12 blue marbles. What is the probability that the first marble is yellow and the second marble is not yellow if you replace the first marble before you selected the second? That's independent if you do replacement. If you do not replace or without replacement, that's dependent. So let's look at A first. The probability that we pick a yellow and then we don't pick a yellow. So we're going to replace it. How many yellows are there? There's 15 yellows. How many total marbles are there? There are 37 times. Well, there's 15 that are yellows. There's 22 that are not. and you end up with 360 out of 1,369, or approximately 0.24. That's our probability of picking a yellow that are not yellow with replacement. How does that change if you do not replace it? Well, it's still the same idea. Probability of y times the probability of not y giving you picked the y. So the probability of y, that stays the same as it was in the last one, 15 out of 37. Now how does this change? Well, assuming we picked one that was a yellow, then that means that there are still 22 that are not yellow left. But since we kept that yellow out, there's only 36 marbles left. So that is the difference. If you keep the marbles out or the cards out or whatever you're picking out, then there's one less to choose from on the next time. And that means we get 55 out of 222. Remember, you can multiply these in your calculator. Sorry about that. 55 out of 222 is approximately 0.247. So the probabilities were they were very close this time, but they were different. So replacing and not replacing, there is a difference in what your final answer is going to be. Okay, find the probability of 3 dependent events. Let's look at that. Your teacher passed around a box of 10 red pencils, 8 pink pencils, and 13 green pencils. If you and the 2 people in your group are the first to randomly select a pencil, what is the probability that all 3 of you select pink pencils? Okay, so the first time we draw, if I go first, then there's 8 pink pencils out of, well, how many are there total? Looks like there's 31. 10 plus 8 plus 13. Now I hand the box to the person next to me. If I got a pink, then there's 7 pinks left, and there's now only 30 colored pencils left. And if that person hands it to the person next to him, then there are only 6 pink colored pencils and 29 total left. So if it's dependent events and we're keeping these things out as we pick them, then the possibilities decrease as you go across. That is approximately 0.012 chance if it's just random. What if it's the probability that all 3 of us select a red pencil? Very similar. There are 10 red pencils, so when I draw first, I have a 10 out of 31. The person sitting next to me gets a 9 out of 30, and the person next to them, 8 out of 29, or approximately 0.029. A little bit higher because there's more red pencils in the box. Okay, so here are our targets. I believe we adjust them, and we're going to reinforce them tomorrow in class. First one, I can find the probability of an independent events with replacement. We did that, independent events and independent probabilities. I can find the probability of dependent events that's without replacement. We discussed the differences between those and how the formula is slightly different for each one. Have this for me tomorrow, and we'll see you then.